we have to be fair for the people who come on time. Once again, I am Dr. Lalit Lienage, IET session chairman, IET Sri Lanka Network session chairman. And today we have our traditional monthly evening forum, which we used to have at Galadari Hotel face to face, but due to COVID-19, we have been shifted to online option. And this is our third webinar from April, May, June. And I welcome all of you. Let others join us. And since we are recording, we will share the entire session among the registrants after the webinar. And we have selected the timely topic, I guess, drone revolution, with the especially with the COVID-19 and social distancing. The use of drones have been extensively kind of increased. And I saw recently an advertisement from Civil Aviation Authority asking all drone users, suppliers, and manufacturers, everyone to provide information to the Civil Aviation Authority, because they are doing a survey about the drone capacity in Sri Lanka. So I think our eminent speaker will talk many things about drones, because he is, if not the most prominent expert, one of the best in Sri Lanka about drones. He has many years of experience, hands-on experience, and vast knowledge in this subject. I will not talk about drones now, because he has a he will have an excellent presentation to you. But let me introduce our speaker today, Engineer Professor Rohan Munasinghe. He is attached to the Department of Electronic and Telecommunication Engineering of the University of Maratua. He was the former head of department. He earned the M.Eng degree in 1999 and the PhD degree in 2003, both in Advanced Systems Control Engineering from Saga National University, Japan. His main areas of teaching and research are robotics, control systems, unmanned aerial vehicles, underwater robotics, autonomous intelligence systems, artificial intelligence, and system optimization. Professor Munasinghe was part of KIST, K-I-S-T, Stanford Research Collaboration on Advanced Robotics. He has won awards at the International Inventions exhibitions in Geneva and in robo competitions of India in many occasions. He has undergone training at Commercial Law Development Program in USA on technology transfer. He has completed training on intellectual property at the USPTO ASPTO, and has completed courses of the World Intellectual Property Organization, the WIPO. He is a member of the National Science and Technology Commission, NASTED, Honorary Advisor to the Vocational Training Authority, Director of the University Business Linkage Center, UBLC, a member of the Senate Research Committee, SRC, and a member of the Intellectual Property Advisory Committee, IPAC, of the University of Maratua. Professor Munasinghe is the chair of the NSF Committee on Engineering, IT and Architecture, also serves in the steering committee of the Center for Research and Development of the Ministry of Defense, which I also was a member. We shared many things in this CRD steering committee, and in the advisory committee of the Sri Lanka Planetarium. He served in the board of governors of the Arthur C. Clarke Center for Modern Technologies, board of directors of the National Engineering Research and Development Center, and NSF committees on technology, science, popularization, and nanotechnology. He is the founder chair of IEEE Robotics and Automation Society chapter in Sri Lanka, and was the chairman of IEEE Sri Lanka section in 2010. Professor Munasinghe is a chartered engineer, senior member of IEEE, member of Robotics and Automation Society of IEEE, and a member of IESL. I kindly invite him to join IET as well, which will be a great value for IET. And with that note, you may have seen his vast exposure in science, technology, and engineering. So without much ado, let me now invite Professor Rohan Munasinghe to deliver his speech. And after the speech, we can take questions from the participants. And I request you to put your questions on the chat session so that we can capture all questions. And at the end, we can take one by one. Otherwise, it will waste time if everyone wants to speak. And the game rule is everyone should switch off your microphones and videos and let Professor Rohan Munasinghe take the stage with his presentation. Over to you, Professor. Professor, your mic is off.
Yeah, can you see my screen?
Yeah. We can see your slide. Yeah.
And thank you, Lalit, for the introduction, and thank you very much for everyone for joining in for this session. It's always a pleasure to me to talk about technology to groups in Sri Lanka to inspire them to do innovations and then develop products, put it to markets, and then generate revenues for the country. So this is the fundamental objective of all these research and development to help develop Sri Lanka. So, and yeah, I will join IT. So definitely, yeah. Right. So the today's topic is drone revolution. Right. Drones are revolutionizing the whole world in various ways. We have been doing drone research for quite some time. I started my first drone project in 2006-07 period as a final year project. And since then, we have been continuously developing technology, drone technology. And today's presentation, I really want to show you the local stuff, Sri Lankan stuff, right? We are a very capable nation. For some reason, this capability doesn't come out for various reasons. We are weak in working together. We are working. We are weak in appreciating others to figure out others' capabilities, and then networking, right, and sustaining our collaborations. So that part is missing in our culture for some reasons. So that is why, even though we have very capable people, we haven't seen much of innovations come into the markets. So innovations and product to come into market needs a lot of people, and that is fundamental truth. Single person cannot do everything, so that is a failure equation. So we need to get together engineers, technologists, laborers, managers, marketing people, politicians in a well-connected hierarchy. Then only we can bring something out to the markets. Unfortunately, it is not happening in Sri Lanka yet. Right, so let me start off with showing you these commercial drone market figures. Commercial drones, I have taken only commercial drones here, right, of the internet. You can see the growth from 2016 up until now, 2020, then the forecast till 2025. So you can see this histogram climbing monotonically, right? And every pillar, if you move upwards, you can see a circle, green circle with a number. That is the value, the revenue in billions of US. So that number also increasing The size you can see by 2025, it is projected to be 12.6 billion US dollars. That is the drone market size, commercial drone market size. Okay, commercial drones. And if you look at the applications where these drones are, right? So what are the major applications? You will clearly see this graph here, right? There you can see 38% of the commercial drones are deployed in aerial photography, aerial videography. That's for sure. You have seen in Sri Lanka also. Small drones, Phantom, DJI, Chinese drone is number one, most popular. And then which is the Mavic Pro, the successor of Phantom Pro. How people getting onto that one. Phantom is kind of discontinued now. So these two drones, basically designed for photography and videography, takes 38% of the market. And then you have the other things, surveying, mapping, GIS. Now, if you ask a surveyor that you want to survey your land, if it is a big land, definitely he will bring a drone. You can see that that is the state of the art for surveying industry, drones, surveying drones. Then you have the real estate, the construction, and then agriculture. These are the 5 main areas, applications where drones have already been deployed, and they take more than half of the circle. You can see the other applications are actually emerging. Like for example, agriculture is emerging. Right now it is about 7%, but I'm sure in the next 5 to 10 years, this will grow. Everything will grow, but particularly agriculture field will be invaded by the drones. There's one thing missing here, that is the package delivery drones. You have seen drones bringing packages. I will also show some of our drones designed for package delivery, delivering a small package to a distance, not far distances, maybe few kilometers, drop the package and come back. That has not taken huge part here, not because of any problem with the technology. It is because occupying the airspace is a serious undertaking. Other owners, like for example, the low-flying military aircrafts are there, low-flying choppers are there, and pilot training is happening. So that is why they don't want to take any risks. Basically, civil aviation in any country, they don't like drones to come into airspace, making necessary problems. But this is just a matter of time. Inevitable situations like drones will fly with packages in the air will happen within the next decade. Then we can see that part also in this graph. Then I just want to say something about going back to this one. There you can see only the commercial drone market, which is about 12.6 million projected to 2025. But if you look at the whole thing, including the consumer drone markets, the toys, DIY, etc., the actual market is forecasted to be about $40 billion by 2024, 2025. It's about 40 billion market within the next 5 years, right? Now, let me show you some of the drone. So now this is becoming now techie a little bit now. There are drone types. The first one over here is a multi-rotor type. So let me show you this video, right? Can you see the video and hear the sounds?
Not yet. You have to click something in Zoom. In your share screen down, you will have something called, I cannot exactly remember, 2 buttons where you need to allow videos to
Yeah. So you don't see the video, right? You don't
Yeah,
see the video.
you have two buttons under your screen from the share computer sound and optimize
Yeah,
screen sharing.
yeah.
Yeah,
I know that. So let me get back again. Yeah. So I already clicked that button. Share computer sounds.
right. And the video, you have to click another button, I think, to share a video.
Yeah, that one is disabled for some reason. Why is that?
I had the same problem when delivering lecture last week to my students.
Hmm. So if I
Uh,
delete,
the two, right. One is disabled, like, no?
yeah, one is disabled.
Uh, our guys, Vindhya, Priyanka, you have any solution for that?
Okay, now fine, now fine. I got it.
All right. Okay.
Right now, see whether you can see the video.
Not yet. We can see the voice. All right. Looks like it's coming. Hold on. Till the screen is blank, we can hear drone
I
sound.
know, I know. Yeah. So each and every video I have to share separately. That's why these are linked videos. That's why. So yeah. So yeah, I'll do this. I have to share
Don't
this.
worry. Take your time, Professor.
Yeah. So now you should be able to see the
Yeah,
video
yeah,
and
yeah.
the
Now it's good. Yeah.
yeah. So every video I have to share separately. Now what you see here is a multi-rotor type of UAV drone carrying a package fully autonomous from a home position and flying to a destination, right? And then land at the destination. Like that, and fast forward into some time and drop the package and then take off again to altitude and then correct the heading to fly back home. So once it comes home, it lands autonomously. So that is one thing. Then the second type of drones or drones is actually fixed wing, like a plane. You have the wings and all, right? So let me show it to you here. Right? But unfortunately, I have to share it again. So can you see the drone and the sound? Yeah, right. So this drone is another locally built drone. You know this place. This is Bandaranaike International Airport. This drone is carrying a camera, 24 megapixel Sony Alpha camera. It is taking photos of the airport, and these photos are connected together to make the entire map of the airport premises. So that is also fully autonomous drone. You plan the mission and then throw it to the space, and the operator, the manual remote pilot, RC pilot, takes it to a certain altitude and then engage the autopilot. And after that, the drone will fly autonomously according to the planned mission. So while it is flying, it takes the photos, and this is how it lands using a parachute. So it is very safe landing. So that's about it. Now, there's another category which is here, this one, multi-rotor plus fixed wings, right? The two earlier versions together. So let me show you this one. Now this is taking off like a copter vertically, right? And when it comes to a certain elevation, it starts flying like a plane. So the entire mission is basically a plane mission, like a plane. So you can send the plane to whatever distance you want, carrying whatever payload, and it will accomplish the mission just like a plane. And when it comes home, it will transit the control configuration to a copter like this. Now it will hold the position in the air just like a copter and then gradually descend down to land. So this is what is called the VTOL drone, vertical takeoff and landing drone. So this is going to be the new drone type, which is becoming more popular than the previous two drone types, right? Now, if you put all these three types together and make a good judgment, the first one over here, very easy to operate, right? So it takes off vertically, lands vertically. So therefore, you don't need a big runway or open space to take off and land. However, it doesn't have wings, therefore it is energy inefficient. As it flies, it consumes a lot of battery because it has to generate equal and opposite thrust that to the weight, and that consumes a lot of power. That is why these multicopters cannot fly long distances. They are basically for 10, 15, 20-minute endurances, but latest battery technology can bring them to about 40, 50 minutes or 1 hour maximum. The second type here, the wing type, everybody knows it. You need a huge open area for landing because when the drone comes for landing, the approach distance has to be there. There cannot be tall trees or buildings nearby. So, but you don't find that kind of open space nowadays, right? Especially in urban areas. So deploying the winged drones, the second type here, is a question in populated areas. But the good thing is that these drones are highly energy efficient, which means they don't need to generate a thrust equal to the weight of the drone. But maybe just 10-20% of that is enough. Just need to push it forward, the wings will generate the thrust. So that is why winged drones can fly hours and hours. So these two types have pluses and minuses, but once you put them together into this third type of drone, you get the best drone, which can take off and land almost anywhere, doesn't need a big open space because they are like copters, vertical takeoff and landing. And also they fly like a plane into the mission. So therefore they are very energy efficient so that you can fly hours and hours. So that is why it is becoming very popular. Now, if you look at the drone capabilities these days, right? The drones have many flight modes. So what are these modes? For example, you can fly them entirely manually, manual control, right? But there are other modes like stabilize, for example. Drone can fly level. And if it's a multi-copter, it can hover at a certain altitude. And also there are other modes like fly-by-wire. For example, when you have fly-by-wire mode of operation, drone will not roll too much to the left or to the right, right? It will maintain stable flight. And fully autonomous flying, which is going from one point to another through number of via points. And auto landing, you don't have to land the plane yourself. You can have auto landing, but there are things that you have to do before the drone can perfectly land itself. And altitude hold, drones can hold the altitude. Drones can loiter. Drones can go around in circles, right, around a certain point on the ground. And RTL, return to launch, which means at any moment of time, you can ask the drone, come home. That's it. Very high level command. Drone will find its way back home, come and land. So with these very high level capabilities, now it's a very smart machine, drones. You can customize drones to various applications with assurance and safety. And also drones have the second bullet here, the fail safe, right? Because when you deploy drones, things can fail, right? Sometimes you don't get the signals with the GCS. Sometimes you don't have your radio signal received by the drone. Sometimes the GPS of the drone will not work or it will be jammed by jammers. So these things are possible. But you can set the fail-safe settings in the drone so that nothing very seriously bad would happen, right? In these conditions. Like, for example, if the GCS fails, you can ask set the condition in the drone to come home. So when the drone notices that it doesn't have the connection with the GCS, it will abort the mission and come home. So nothing bad will happen. And also when the drone understand, oh my God, the radio connection is not there, the drone will come home. But you have to make that settings. So that is why some people don't do that properly. That is why the Civil Aviation Authority in Sri Lanka and all the other civil aviation authorities in other countries also bit reluctant to relax the rules for drones, because people don't stick to the rules and regulations and do it properly. Some people can fly drones without any failsafe, right? And one day it will make a big damage to somebody. And also GPS. When the GPS glitches are there, you can ask the drone to hold the position. You can't ask the drone to come home because without GPS, drone can't do that. But else, you can ask the drone, okay, stay where you are. I will come and get you, right? So all these fail-safe settings can be pre-configured. So professional drone operators, they stick to these rules and regulations, and they don't make any threat to anybody. And in the recent times, if you look at the technology, how it has been developed, collision avoidance has been added to the drones. Some of the Chinese drones, they have these collision avoidance drones using sonar, LiDAR, and infrared. Okay, so what they do is that as the drone flies, they look forward to any obstacles nearby, usually short range, not far obstacles. We don't consider them as obstacles. When they only get near enough, they become an obstacle. They are detected, and then you can ask the drone what to do, or push back, stay, stop, or whatever. that feature is already there. And then more recent times, last couple of years, vision-based landing and machine intelligence and big data connectivity, these are the areas where people are now trying to connect with the drones. Like, for example, if you have a big data connectivity to a drone, right, you can make the drone very smart, and it has all the information about whatever area, maybe forest, maybe transportation, maybe construction. Um, drones can take decisions and deploy themselves. And also using machine intelligence, drones will be able to figure out people on the ground, can locate suspicious activities on the ground, and then communicate it to the authorities to take decisions. And also using vision-based landing, drones can be made capable of landing autonomously on a certain point, even without any GPS. So these capabilities are on the horizon now. They will be incorporated to the drones within the next decade. So if you are a drone hobbyist, if you want to build a drone, these are the 3 steps you have to follow. You have to first achieve the stabilization stage, which means if it is a fixed wing drone, it should be able to fly level, right, without your intervention. When you release the sticks on the remote controller, right, and you set it to stabilize mode, it should be able to fly level, right? It doesn't climb, doesn't descend, no rolls left or right. It should fly level. And if you are doing a multi-copter, it should hover, right? It should keep the position, doesn't move left or right, forward, backward, doesn't drift, keeps the position. It doesn't come down or go up. So that is the basic thing you have to do. And then on top of that, you can have the navigation loop, which is at a low frequency, operating at a low frequency, like 5 hertz. Whereas the stabilization has to happen at a faster rate, like 50 to about 300 hertz frequency. In the navigation part, what you do is, so you instruct the drone to go from here to there, right? Point A to B, like that. And drone will follow using the GPS, right? When you have this stabilization and navigation capabilities, you can think about the other things also: auto takeoff, auto landing, loiter, etc. Then you are ready to deploy the drone for application. So what are the applications? It can be aerial photography, videography, can be a surveying mission, maybe agriculture, so looking at the crops, whether they are healthy or not, surveillance, delivering a package, or inspection of a pipeline, traffic estimate on the roads, various applications. So when you deploy the drone for an application, right, you need to have hardware, software development on top of the basic drone, that is stabilization and navigation. So let me now tell you a bit more details into this stabilization and navigation part, right? Maybe you want to know how it happens, right? So there you can see a drone, a multi-copter, and the 4 motors, brushless DC motors, and their electronic speed controllers. These yellow ones are speed controllers, right? Now, by combining the speeds of these 4 motors, you do the maneuvers of the drone. Like, for example, if you have these all 4 motors running with high level of power, the drone will climb. And if you reduce the power of all 4 drones, all 4 motors rather, the drone will descend down. Okay, and that is what is called the altitude loop. The green box here, lowest one, altitude. Now, if you increase the power of the 2 motors here and reduce the speed of these 2 motors, right, the drone will pitch up. Pitch up. There's a pitch loop over here, right? So if you reduce the speed of the two front motors and increase the speed of the two rear motors, the drone will pitch down, which means it will move forward. So that is a pitch loop. Okay, so I can go on and explain you what happens if you do the other way. Like if you increase the speed of the two left motors here and reduce the speed of these two motors on the right, the drone will pitch to the right. Okay, roll to the right, right? Then it will move to the right. So this way you can make the movements of the drone forward, backward, up, down, left, right, right? By controlling the roll loop, pitch loop, yaw loop, and altitude. By the way, this yaw loop, when you change the heading, what you do is maybe you can increase the speed of these two motors, right? Opposite sides, and reduce the speed of the other two motors on the opposite side. Then what you do is you control the heading of the drone, right? You turn from east to the west to northeast like that. So with all these four control loops, you can do whatever you want to the drone. Okay. Now, who is controlling all these four loops? It is the flight controller. So here what you see is a locally built flight controller, our own flight controller. We built this in 2012 as one of the final year projects. And we flew a small fully autonomous drone with this flight controller to verify the accuracy. So the flight controller can stabilize the drone. Now, if you want to do the navigation and put it into an advanced mission, you need to have additional sensors. Like, for example, you need to have a GPS, right, interface to the flight controller. And you need to have a compass interface to the flight controller. So compass will help the flight controller to change the direction, heading. GPS will let the flight controller know the position. And also you can have a sonar if you want to detect the altitude in low altitudes. When you do the landing and takeoff, sonar will come in handy. Even though there is a barometer, semiconductor, solid state barometer here, you can have additional sonar here. And also if you want to see the airspeed, the flying speed, you can have the airspeed sensor here, right? Even though you have the GPS telling you where you are, your position, and by differentiating, you can calculate the speed, the ground course. In addition to that, you can have a intrinsic speed measurement using the airspeed sensor. And also, if you want to control the drone, you need to have RF receiver attached to the flight controller. So through the RF receiver, you send your commands, remote controller commands, roll, pitch, yaw, to the flight controller. So when the drone is in the air, it is moving, right? The parameters, variables change, the speed, altitude, roll, pitch, yaw, the currents of the motors, etc. They all can be communicated back to your ground control station. This is where you can see what the drone is doing, the whereabouts, everything. Okay, so this is simply all what you know about the internal hardware arrangement configuration of a multi-copter, multi-rotor drone. Now, if you do a winged drone, a plane rather, nothing will change except the drone, right? You can see here the same roll, pitch, yaw, altitude loops are there. And now this time you have aileron, elevator, rudder, which means the commands of the roll loop, that is rolling left and right, will go to the ailerons. The pitch loop, which is climbing up or down, will go to the elevator, right? And yaw loop, turning left, turning right, the heading correction will go to the rudder, right? Actually, rudder and aileron both. Altitude loop will go to the throttle, the power of the motor. So others will remain unchanged. Okay. Now let's look at the applications. And you saw that the number one application of drones today is aerial surveying. So therefore, that is why we also in Sri Lanka, when we develop our drones, once we have developed the core drone technology in Sri Lanka, the first application we targeted was also drone surveying. So there what we do is, let's say you want to create a survey map of this area, the top left figure here, right? This is the area you want to survey, right? So we plan the mission like this. This yellow lines are this is a path of the drone. So it flies zigzag, right, like that, uh, while taking photos. And on the right hand side, you can see the photos taken. See, there are so many photos taken. You can see the photos are not on a straight line because this is the path of the drone. It doesn't go straight line, right? Because the crosswind and all, it moves back and forth, sideways. However, when you take the photos, you make sure you can see it here in this photo, the two positions of the drone, the blue one and the red one. When it takes the photos, there's a huge overlap between consecutive photos, such as about 80% of a photo taken at a point, right, will be recorded in the next photo also. So 80% overlap, forward direction and also lateral direction is about 75, 70%. So therefore, because of this huge overlap, right, you can see on this photo here, there's a single point on the ground, maybe a piece of rock, right? And you can see these green lines going to the photos, which means all of these photos, right, to which these green lines are connected, they have this piece of rock in there. So you can see there are so many, maybe like about 20 photos, right, in this collection has this particular rock in there. So huge redundancy because of the huge overlap. So when you put all these photos into a computer, by the way, these photos are actually geotagged, which means when the photo is taken, the drone will write the GPS coordinate, right, where this photo was taken. So the processing software knows roughly the location of the photo. So it will arrange the photos accordingly and then look at the images. Then the software will understand, this particular rock is seen by 20 odd photos here. So then they will arrange the photos precisely, change their direction, orientation with respect to each other, the neighboring photos, and create the big maps like this that you see here. This is a University Moratuwa map. It is not just one photograph. It is created using more than 600 photos, And there you can see another one, a landslide in Aranayaka. Remember the landslide happened there, the deadly one. More than 100 people died. This is that landslide. This was created by our own drones using some 400 photographs. Okay. So once you create these photographs, you can also create what is called the contour map. You can see it over here. This is part of Kantale Sugar Corporation, right? Recently we did the map, not recently, a couple of years back, the contour map for Kantale Sugar Corporation using our own drones. And this elevation map here you can see is very important for the engineers, the irrigation and civil engineers, to plan their roadways, the waterways, the buildings, etc. So the technology is in our hand now, the drone technology. So let me show some of these videos. This one. Again, I have to share that with you. You can see the map, right? Can you see the map?
Yeah, we can see.
Right. Okay. So this is collection of some 600 plus photographs, right? And then the mosaic created. So this is University of Moratuwa. You can see the ground, and this is electronic department where I am located right now. So our main building, Sumandasa building, the library. This is a very high precision map, a survey map. Using this one, you can take measurements, any distance of a roof, volume of a certain roof, right? Areas, what is the ground area here, right? In acres, to a very high precision, you can take the measurements. Right. Then let me show you another one. That is this. This is Aranayaka landslide. We deployed one of our drones to map the landslide. So this is the top of the mountain, and this is where the mud slided downhill, disappearing, making the building, the houses, everything disappear. So using these maps, you can take the measurements. That is the important thing, the distances, the areas, and also volumes. You can see this photogrammetry, right? It's not very precise in constructing. You can see these trees and all are not precisely constructed, right? But the idea is not to reconstruct the whole thing precisely, but to make the aerial map precise, right? To take measurements, distance, areas, and volumes. Right. Now, there's a new technology coming to the drones. That is what is called the RTK or PPK. RTK stands for real-time kinematic. PPK means post-processed kinematics. So remember the two words. I'm trying to let you know not only just drones, but other technologies that are getting connected with the drones. Eventually, drone becomes a vehicle, right? It's just a means. On top of that, you can put other tools and you can deploy it for a certain application. So there on the left side photo here, you can see, by the way, why we need RTK, PPK? This is basically to increase the precision of position information, right? You know that if you use a normal consumer grade GPS, right, and if you keep it on your hand, you get a number, right, latitude, longitude, and you can convert that into meters using a certain geodetic coordinate frame, right, and you get your position. So this position can be erroneous as big as about 5 meters, plus or minus 5 meters. So that is the accuracy of a consumer grade GPS. Now, if you think that if you have 5-meter plus or minus error in your photographs, right, taken by a drone, and when you put them together and create the map, right, you cannot expect a better accuracy, okay, unless you use very high precision position measurements on the ground. So the surveyors do that. They don't depend on the drone photography, right, alone, but they put marks on the ground and they capture those marks on the drone imagery and go to those points and annotate those points with very high precision coordinates using total stations. I think you know that, right? Then they re-optimize the map so that it will become more accurate. Now, you don't have to do this if you have RTK, PPK, because RTK and PPK will give the drone, right, that accuracy right away. So this is how it works. So when the drone here on the left photo, right, has this RTK or PPK GPS, right, it will always communicate with the ground station or base station. So these are small devices, like for example, like size of a matchbox. The RTK sensor with about 100 square centimeter antenna, right? A flat panel of metal, maybe aluminium foil. Just that. So these units are receiving information from the GNSS, the satellite, GPS satellite network, or any other GPS network. And the total station here, the base station here, is a known point. So it receives these signals from the satellite network and it knows the error, right? The satellites say a certain position, but the base station knows its position accurately. So it can calculate the error. Once it calculates the error, it can communicate to the drone the error, so that the drone, like error means easterly or westerly or northerly or westerly, southern. So all these two directions, right? Left, right, up, down. How many meters is the error right now? So drone will immediately correct that error and geotag the photos accordingly. So that way you can increase your accuracy to about 3 to 4 centimeters. So that's a huge improvement, right? So your survey map is as accurate as 3 to 4 centimeter plus or minus. So that's a very good achievement. Now, if you cannot have this RTK configuration where you have a total station communicating to the drone in real time, right? You can do the PPK, post-process kinematic. There, what you do is you have the one unit station on the ground, keep collecting data, and the drone has another unit collecting the same data, okay? And after the drone flight is completed, you bring these two files together and put it to a cloud process where this correction is calculated using not only these satellites that you see there, but all the other ground stations nearby, like a network, for example, right? Not only this local station, there can be so many other local networks which are receiving the same information, same time, and you can do a much better correction, right? The corrections are because the errors of the GPS is basically because of the atmospheric problems, right? Rainy conditions, cloudy conditions, temperature, and all these things will introduce this 5-meter error in the position. And now with the post-processed kinematic, you can finally, smoothly do this process, the workflow, so that you calculate the positions very accurately. So this is what we are doing right now at Morotour PPK geotagging, so that our drones can generate very high accuracy maps. So let me show you another video clip here, right? This one. So this small drone is actually really advanced stuff. There you can see the camera and all. This has a post-process kinematic GPS (PPK). So when it flies, it will collect that position information as a separate file. When it comes home, we get the images and that position file and communicate it with the other file generated in the base station, and we do the post-process kinematic to improve the accuracy. Yeah, so we have developed the drones including PPK technology. So that is a serious development. Now, this one we named Seahawk is more than a drone. We call it unmanned aerial vehicle, right? This drone can have about 3-hour endurance. It's a medium range UAV. It is powered by a gasoline engine, right? And it can map about 120 square kilometer per flight in that area, right? 120 square kilometer can be mapped in single flight. So if you look at the entire Sri Lanka, right, leaving out the jungles and other things, if you really want to map a survey map of Sri Lanka, you need to have 416 flights of this drone. Okay. And if you have, let's say, a 5 drone fleet, 5 of these drones, so it is about a 3-month work. So entire Sri Lanka can be mapped within about 3 months using 5 of these drones. So this is the power of drones. And now imagine usual surveying. If you want to do in entire Sri Lanka, how long does it take? It has never happened in Sri Lanka, by the way. So it is extremely difficult. People have to walk on the ground, very difficult, accessibility, right? And making this surveying using poles and theodolites extremely difficult. Now the drones have changed the landscape entirely for surveying, and now nobody is walking on the ground, but drones are deployed to take photos, and then the geotagging using PPK or RTK technologies, and on the computer you generate the map with very high precision. So this is what the drones can do for aerial surveying. Now we have taken it forward from this point, the Seahawk, to Hornet. This is the Hornet, which is under construction right now at Moratuwa. Because of the COVID, we had to temporarily hold this project. It's only now we are beginning to we are resuming the work. You can see it's for international market basically, not for Sri Lanka, right? This one is also the same. Sri Lanka is too small of a market for this kind of high-tech products. We have to target the region and the international market. So this is a VTOL drone, whereas this one is not a VTOL drone. You don't see any quad mode motors here. It's just a plane. But this one will carry propellers here, vertical propellers here and here to give it a vertical takeoff and landing. And there's an engine here, petrol engine, to push it forward like a plane, so that most of the mission, it will fly like a plane. And there you can see the payload bay here is a sizable payload bay. We can change the payload to a camera if you want to do a aerial surveying mission there, or if you can have a package if you want to deliver a package, maybe some blood packets or test swabs in case of COVID, from a collecting center to the testing center. So there are many applications, and it will have about 3-hour endurance. It's a long endurance flight, so which means you can take it off from maybe Ratmalana and land it in Jaffna. Now the other emerging application for drones is agriculture. So what does the drones do to agriculture? It's basically like this. We are talking about huge agricultural lands, paddy or corn or whatever, right? It's impossible to monitor the stress plants in a huge area manually. So you can deploy a drone like this, for example, with some sensors on board, So the drone flies along this over the crop field, huge crop field, collecting images, right? And then you process those images on a computer very quickly. And then let's say you can figure out what are the good plants and the weak plants, healthy and unhealthy plants. Then you know their locality, you know, which area has weak plants. Then what you do is you deploy another drone, like a copter kind of drone here, with a tank of full of fertilizer or maybe pesticide, weedicide, whatever required chemical. It will reach out to those spots, right, and spray the required amount and come back. This is the clinical delivery of chemicals in agriculture without just spraying all over the place and not knowing what are the good plants, what are the bad plants, right? This technique will figure out what are the weak plants and deliver right amount of fertilizer to that location. So we call it precision agriculture. So let me talk about this agriculture going out of drones to the technology where we can differentiate the healthy plants and unhealthy plants. Now you can see this spectrum here starting from 400 nanometers to about 850 nanometers, right? And the green line is for green vegetation, which means healthy vegetation. And the red line is for the stressed vegetation because of a disease or something, or not having enough water or nutrition. The red one is not healthy. Now, if you look at the visible spectrum up to about 700 nanometer, the two lines are closely apart, right? You can see red one is up a bit from the green one, but not seriously noticeable, right? But if you cross the 700 nanometer area, of course, the light is not visible here, but you can see a marked difference between the stressed plants and the healthy plants. So therefore, just by looking at the plants, you can't tell for sure about the health of the plant. If you want to tell about the health of the plant, you need to look at the invisible area. Okay. So we developed a drone for this purpose, a very small drone. With this small sensor here, you can see slightly bigger than a box of matches, right? And the drone has the flight controllers, the parachute and everything. And by the way, this one is the sensor. The top right photo, you can see the small box looking downward is the sensor. It's a multi-spectral sensor. And together with comes this small part here, another box kind of thing, which looks upwards, not downwards, right? This is the sunshine sensor. It tells you the strength of the sunshine, because this is photogrammetry. You're taking photos and looking at the plants, how much they reflect light, right? You need to know how bright the sun is, right, at that moment. Otherwise, your measurements are not correct. So if you look at the sensor, down here, you can see it has 5 cameras, 5 miniature cameras. It has red edge, which is 735 nanometer. You have red camera, 660 nanometer. You have green camera, 550 nanometer. You have near infrared, that is 790 nanometer. The green and red are visible, but red edge and NIR, they are not visible. They are above 700. Okay. So you are collecting this information, 2 visible wavelengths and 2 invisible wavelengths. These wavelengths, if you put it on this graph, you can see the green is here, red is here, right? And the red edge is here, and this is near infrared. Okay. Now you take a series of photos, a collection of photos, just like when you do a surveying mission, right? You take overlapping photos and then you combine the photos together, create the mosaic, right? The map. And this time you are doing it for 4 different colors: red map, green map, red H map, and near infrared map. Okay, so in addition to that, you can have the normal RGB camera that is over here, that is also there. So this is the mission. When the drone flies with the multispectral camera, it flies like that, collecting images and comes home. And after that, we take the SD card out of the camera, put it into the computer, download all the images, geotag them, and then combine them together using the features on the ground. So this is the collection of photos, right? And now we come to mathematics, right? Now, if you look at these two trees here, plants, right? The left one is healthy, right one is not healthy, okay? Now, the healthy plants, if you look at the near infrared and the red, for example, just for an example, right? The healthy plants emit about 8% of red light and about 50% of near infrared light. Okay, this is average. Versus a near infrared stress plant, right? Not very healthy plant, which emits about 30% red, about 40% near infrared. All right. So there's no question about it, right? Because healthy plants don't emit too much of red because they don't look red. Okay. Whereas unhealthy plants look more red. Okay. So that is our observation. But if you go to science, photosynthesis absorb a lot of red light. So therefore, good plants which are doing photosynthesis well do not reflect red light much. Okay. So either way, you know it. Now, if you look at this equation, NDVI, maybe some of you guys have heard of it. Normalized difference vegetation index, right? This is the equation, NDVI equation. So what is that? It is a ratio between NIR minus red and NIR plus red. Just that, very simple equation. Now, if you put that onto a healthy plant, right, what would you get? NIR minus red. So NIR is 50 minus red is 8. 50 minus 8 divided by 50 plus 8. So that is 42 or 58, about 72% or 0.72. And if you do the same for a stress plant over here, right? NIR minus red, that is 40 minus 30. 40 minus 30 divided by 40 plus 30. That is about 10 over 70, 14%. Now see the difference, right? So by combining this reflectance of different wavelengths, you can calculate the NDVI so that you see for healthy plants, NDVI is higher. For stress plants, NDVI is lower. So you clearly differentiate on your crop field, maybe it is tea, paddy, corn, whatever. Where are the healthy plants? Where are the unhealthy plants? Okay. So when you put that onto your computer, you will see something like this. You can now assume false colors to the map, where green areas are high NDVI, red areas are low NDVI. And for sure, these red areas, there's something wrong with the plants and you need to take action immediately. If you can take action immediately, water these areas, so put some nitrogen, whatever, and then after about a week, you can do the mission again and see how these red areas have turned into green areas. So if you do this for a season, closely monitoring the crop field, you can maintain healthy plants, right? Mostly healthy plants in your plantation. Eventually, at the end of the season, you get a big harvest yield. Okay, so this is proper crop management using drone technology. So once you know the red areas, right, now you can have a drone with a tank full of fertilizer, right? And to the drone, you can feed this information, uh, this red information areas. Okay, so drone will fly over the red areas only, not over green areas, and spray the right amount of fertilizer. Okay, so this way, so what is the difference you are going to introduce to the field of agriculture? First, you reduce chemical usage. Now you are not spraying all over, right? You spray wherever it is needed and the right amount, because you can see this red color intensity, which means if it is bright red, which means more nutrition is required, more nitrogen is required. If it is not very intense red color, then you know you need to spray a little amount. So this way you can adjust your spray speed and save your chemicals, right? When you reduce your chemical usage, you reduce the human exposure, right? For two reasons. When you deploy drones, there is no humans involved, so no exposure. Even though people are there, the exposure will be minimal because the drone will spray only the right amount. So no health hazards, right? No water contamination due to chemicals overdosing, and reduce cost of production. Okay, the labor cost is reduced, chemical cost is reduced, and also because you keep monitoring your crop field, making sure most of the plants are healthy, you get a higher yield, right? Production goes up, and you don't pollute the environment, you don't overdose the soil, so you make it sustainable for agriculture and also good health. So there are so many good things about this, right? So therefore this is extremely important that we introduce drone technology for our agriculture. So I will skip that. Then let me take sample delivery drones, right? Drones are coming into the airspace with packages sooner or later, right? Sooner rather than later. This drone that we developed at Moratuwa, we initially did it for Kottayam Defense University, and we are building a second drone of this one. We are working with the medical people to make it deliver test swabs. Like you can see it over here, about 20 test tubes, right, with some test swabs in it. You can transport from one place to another. We are in early stage of development, but some promising results have already been obtained. So let me show you this video of our delivery drone. Right. So this is another VTOL drone, right? Vertical takeoff and landing drone. When it comes to the elevation, it will fly like a plane. You can see it here in a moment. So now it is flying like a plane. The quad rotor motors are not working anymore, just a plane. It goes to the destination carrying this package, small package. So when it comes to the destination, it will hold the position in the air like copter. You can see it in a moment. And then drop the package using a parachute. Like that. You can see the parachute coming down. Somebody can catch it, and the drone starts going back to home location. And once it comes home, right, you don't have to do anything. It will hold the position again at the landing spot and then land smoothly like that. So that technology is there. So we are trying to commercialize some of these technologies for the benefit of Sri Lanka. And this one is another package delivery drone, but this one is more closer to being commercialized, right? It is a multi-copter drone with 8 propellers, and it can deliver a package to a destination fully autonomously using a thread. So let me show you that video. So now this video starts with the mobile application. So you use this mobile application and you log into your online shopping store, right? Uh, and you are the customer, and you go to the store, you pick up what you want, and you want to purchase this jacket, right? When you place the order, you pay money, and then you say, I want it to be delivered by a drone, and you mark your location, right? This is my home location, deliver. And you also can set the time of delivery. So your home at this time 3:46, I want the package to be delivered 3:46. Order is confirmed, and then in the back end, the online store will have the warehouse where there's a drone, and somebody will attach the package to the drone, and drone has all the information where to deliver, takes off. To the destination autonomously. As it flies, the customer can check, just like you see your pickup, pick me or Uber is coming to pick you up. Very much the same way you see the drone is coming to your location. So you can go outside to a little open area and wait for the drone to come. So when it comes to the destination, when the drone comes to the destination, it will confirm with the recipient, the customer, if the package can be delivered. So once it is confirmed, the package is delivered using a thread. The drone doesn't land in unknown territories, right? But using this thread, it will deliver the package, and after that it will release the thread and fly that. Right. So now the drone flies. So while all these things are happening on the ground, the online store can monitor the process, whether the package has been delivered, whether the customer is satisfied or not. Right. So this is very close to being commercialized, and we are looking for partners just to be able to take it commercialized. Okay. So that is the end of my presentation for today. I need to make some time for your discussion also. So now let me summarize, wrap up the talk today. So the first point I want to stress on is that drone technology and the capabilities have developed very seriously over the last decade. And they are now very promising tools and means for various applications. aerial surveying, agriculture, delivery, disaster management, etc., etc. So there's no risk today if you stick to proper practice with the drones. The risk is very minimal. Okay. The second point I want to stress is that drones have been historically military tools, right? Not for university research teams, not for public, but not anymore. Thanks to the serious developments in the enabling technologies like electronics, computing, communication, etc. These technologies have developed very seriously over the last decade. Now there are electronic components, very accurate and affordable, cheap, right? And there are communication modules which are very fast, small in size, lightweight and affordable. And there are embedded platforms like Raspberry Pi or STM, whatever. You can program things, and these things are very lightweight, consumes least amount of power. You can put it on the drones and develop your application, right? Drone is just the vehicle, and application is running on these embedded platforms. So thanks to the development of electronics, communication, and computer technologies, the drones have come out to the universities and the public in general from their original places of birth, like in military. And the significant maturity that technology has reached today in terms of sensing, controls, and also fail-safe is remarkable. And also recent times, as I explained previously, collision avoidance technologies and connectivity to big data platforms, right? And vision-based landing and navigation. And in the near future, drones will be very, very smart tools, right? So while this is happening in the world, I'm proud to say that Sri Lanka also catching up very fast, right? So we are actually competing with the rest of the world in terms of drone technology. So something we can be proud of as Sri Lankans. And we are hoping that Sri Lankan drone technology can be deployed very soon for Sri Lankan applications, and not stopping there. We want to bring our technology, made in Sri Lanka brand, in the drones to the region and the international markets. So that is our hope. We are working very hard to achieving to those goals. So that's about it, my oral part of the presentation. Over to you for questions and answers. Thank you very much.
Thank you, Professor. It was very comprehensive and very informative presentation. You have put a lot of effort to bring all the real-time videos and to explain the drone cable. It's very interesting. Especially the applications are very interesting because you are hands-on on this subject, and I know you even demonstrating your drones in many national exhibitions, national and international exhibitions at BMICH, so I can remember them. I am very grateful for accepting my invitation to do this presentation today, Professor. And
my pleasure.